Hello.
Hello,
Hello.
sir.
Yeah.
Good afternoon, sir.
Good afternoon. So, good. So maybe we'll start in another 4 or 5 minutes. That's other people join. But not. I mean, around half of the class has not come. So till then time, tell me. Any doubts about stuff that was done last class? Any questions? Any regarding this course or any material that was covered?
Yes, sir. One that is proposition of equivalence class. Proof.
Right. So the proposition this of the equivalence classes, right?
Yes, sir.
The fact that it equivalence classes partitions the whole thing into partitions the set. Correct?
Yes, sir.
Yeah. So you want a formal proof of that, right?
Couldn't know the proof.
Huh?
I couldn't understand the proof.
Oh, you could not understand the proof. What did you find? What did you see the proof actually?
I couldn't do the proof.
Oh, you cannot do the proof. Okay. So let me kind of try to let me share my screen and then I will be able to do something like this. You guys see my screen?
Yes, sir.
Okay. So, okay. So what is it that we want? Okay. So let's start with it. Okay. So this is a. So we have this. We have a equivalence relation. Okay. So let's S be the set, and this tilde be an equivalence relation. Relation on S. Now, what we want to say is that, okay, that if you look at the set of all, so okay, what is this statement? Okay, so this is a theorem. Okay, so okay, so maybe we should start with the definition. Let's start with the definition. What is the definition? What is this thing? That for any x in S, the equivalence class of x, say denoted E of x. What is this? So this is all the set of y's such that x is related to y. Okay? And theorem basically says that the equivalence classes partitions the set S. So what does this means actually? Let's try to understand. Okay, so this basically means that, okay, if, okay, first of all, it means a few things. Number one, union over the all the equivalence classes of X, this is the whole set S. Okay. Secondly, okay, the idea is that two equivalence classes should not intersect. So it is partitions. Partitions meaning, so if this is the set S that we have, and this is an equivalence class, okay, so this is an equivalence class of X, then equivalence class of Y, it can be something which is completely disjoint from Y, but it cannot be something like this. Okay, it cannot be something which intersects both of them. Right? It's an equivalence class completely separate. So in other words, what we want to say is that, okay, if, so this is a partitions means that if X is not equal to Y, then either equivalence class of X actually is equal to the equivalence class of y, or the equivalence class of x does not intersect equivalence class of y. So that means this is equals to empty. Okay, clear? Okay, so if this is clear, then okay, so now, so this is what we need to prove. Okay, so this is what we need to show. Okay, so this is the statement, what means that the equivalence class of x's, equivalence classes partitions the set x. So now let's try to prove. So what else you have to prove? Okay, first of all, see. Hello? Yeah. So I request you all to keep your things muted until and unless you want to ask me some questions. If you want to ask me a question, of course, unmute yourself and ask me a question. And once you get your answer or something, then mute it yourselves, else it will be a disturbance for everybody in the class. Okay. So first of all, let's try to prove this first statement. How do you prove the first statement? Any ideas? Someone can give me a suggestion? How to prove the first statement? So the first proof, I want to show that union of this is equals to S. Yeah.
So we can show that the left hand side is a subset of right hand side and vice versa.
Okay.
Left hand side is epsilon. No, can you say? Okay, I need I don't hear you. There's a disturbance that was there.
So we can show that the left hand side is a subset of the right hand side and vice versa.
Right. Okay. Good. Okay. So in general, if you have to prove that a set A equals to set B, in general, A equals to show A equals to B, it is enough to show that A is a subset of B and B is a subset of A. Right? So maybe this is what you want to do. Correct? Okay. So let's see which one we want to do. So say that I take an X, which is in the union of, so maybe Y, which is the union of this. Okay. We have to show Y is in S. Right. Now, this is one step. This is okay. And the other step is that, right, that for every Z and also, and for let Z is in S, we want to show Z is in union of E of X. Now, see, this is actually the very correct thing to do, and this is how one would like possibly in general to go about it, okay? Or proving something. But again, sometimes you don't have to go into this formal stuff and proving it exactly like this. For this setting, there is actually, so this is, you can do it like this, okay? There's no doubt about that. There's actually a slightly more easier way to see it, this particular statement. How? Okay. First of all, so there are the properties. I will just note various properties of E of X. First property is that E of X is a subset of S. Because this is by definition, right? Because E of S is actually all the y's such that, so all the y's in S such that X is related to Y. So this statement is by definition. There's nothing much to be done. And therefore, you can immediately say that union over E of X. So this is for all X. X is a subset of S. Okay. So this statement, which is basically one half of it, is kind of obvious how to do it. Now the other half, okay, one thing that I can first, this is also another property that you can think of. Okay, so this is a property and this is an observation. This is what follows from it. That for all X, X is a element of E of X. Now this is the first time I am going to use the property that E of X is an equivalence relation. Okay. So why? Why is this one? Can somebody say why is this statement is
Because
true?
it's reflexive also.
Reflexive relation.
By the fact that this is a reflexive relationship. Why is it reflexive? Because it is by definition, because it's an equivalence relation. An equivalence relation better be reflexive also, right? X is related to X, and therefore X is an element of E of X, right? So what can I say? So this is a property that union of E of X, right, yes, contains, now since E of X contains this set X, every E of X contains this set X, X is in S, and this is by definition equal to S. Okay? So this is equal to S. So this implies that E of X equals to, sorry, union of X is in S, this is equals to S. Good. So this one was the easy part in some sense. This was the first property, okay? This first property. And notice we have just used the reflexive property of equivalence relation, nothing else. Okay, now let's see this part. Okay? This is slightly involved. Okay, so how do you prove this? So what we want to prove? So second second part, right?
Hello.
Yeah, hello.
Sir, can you please repeat this as reflective thing once more?
Oh, this reflexive thing. Okay. So what is this quantity? This is what is this? This is an equivalence relation. So what is an equivalence relation? By definition, an equivalence relation is something that is reflexive, transitive, and symmetric. Right? So I'll just focus on the reflexive part of it. So that means this is of course reflexive. This relation that we have is reflexive. What does it mean by this being reflexive? It means that X is related to X. And if X is related to X, let's see this definition of E of X. So it's all this Y such that X is related to Y. Now if X is related to X, that means X is in, satisfies this property. So that means X is in E of X. Okay. And now, since X is in E of X, let's look at the union over E of X. Now, if I have a union of some set of things. Now, every set I can throw away some elements, and then in that case I will have a proper a subset of the, not proper, but a subset of this whole thing. Since X is a subset of E of X for every X, so union over E of X is a superset of union over X in S. And what is the union over X in S? What is the union over all the elements that you have? Is exactly equal to all the elements that you have, right? So we have this is equal to S. So we have this is a subset of S. So maybe this is not how I should write it. This is less than or equal to S. And from, so I kind of jumped here, maybe that's what confused you. Yeah. From this statement and from this statement, we can see that E of X equals to X. Okay. So which implies from both these statements that union over E of X, X is in S, is equals to S. Is this clear now?
Yes, sir. Good.
Okay, good. Good. So in the second part, what do you have to prove? In the second part, okay, so we have to prove that if X is not equal to Y, then either E of X is equals to E of Y, or E of X is disjoint from E of Y. Now this is actually the more trickier part. So how do you go about it? So if you have to prove that either this or this, so one way of proving it is that, okay, so let E of X not equal to E of Y. So this statement says that if this is the case, then either this happens or this happens. So if I say, oh, this does not happen. If this happens, I have nothing to prove. It happens, so go ahead. But if this does not happen, then it is enough to show, enough to show that these two are disjoint. Right? So this is a kind of a same formulation of this statement. So if X is not equal to Y, actually I don't need this X is not equal to Y, forget this not equal to Y. So you can forget this part also. Okay, because if X is equals to Y, we know that it is if E of X is equals to Y. So either E of X is equals to Y, so for all X comma Y, either E of X is not equal to Y, or E of X and E of Y are disjoint. Fine. So this is what we have to show. Right. Now, how do you show this?
So we can use transitive property.
Right. We will use transitive property. But so you're right, completely right. This is what we will use, and we will be using not only transitive. I think we will have used symmetric property also, or something like that. But more importantly, but to go about it, formally way to write it is to, okay, let us prove by contradiction. Okay, what does it mean? It means that let E of X is not equal to E of Y. Okay, this is the initial assumption, and E of X intersection E of Y is not equal to empty, means it has something in common. Then I want to show a contradiction, or what is the contradiction? I mean, I will explain these things more formally as we go to a false statement. Okay, good. I mean, that is like, I think whatever I'm doing, it is something that you have done a million times in your high school. So there's nothing that I'm saying new. Okay. So, but maybe you have forgotten it. So just this is for brushing up your stuffs and all. So let's see, okay. So let E of x, so let Z be inside E of x intersection E of y. Okay, I know that Z is not, I mean, since this is non-empty, so I know that there exists such a Z. Okay, so what does it mean? So now here is a collection of things. Because Z is in E of x, so I know that x is related to Z. I mean, this is why. This is because Z is in E of x. Okay, and I know that y is related to Z. Why? Because Z is in what?
Because Z in the intersection point, so it is also related to
Right. E of y, right? Okay, maybe I made a mistake with this whole things. Okay, forget this. Okay, we need some more explanations. Okay, this is right. Okay, this is completely right, whatever we have done. Okay. So see, this is what we are assuming, right? We are assuming this and this. We are assuming two things, this and this. So because of this, we can assume that there exists a Z which is in the intersection. But because of this, what can we assume? Right? So because E of x is not equal to E of y, what does it mean? There exists a, say, W in E of x such that W is not in E of y. Okay, so this is all the properties that we are slowly getting. Right? So what does it mean? This statement means that x is related to W. What does this mean? Y is not related to W. So these are the three things that we have. These are the four things rather, right? So maybe if I mark it out, I have this statement, I have this statement, I have this statement, and I have this statement. Now let's see. Can we see something? Okay. Say y. Y is related to Z. We know from this property, right? Z is related to x. Why? This is because x is related to Z and this one is symmetric. Right? If it is symmetric, x is related to Z implies Z is related to x. So Z is related to x. And x is related to W because of this. Correct? So what do we have? X, y is related to Z, Z is related to x, x is related to Z. Then by transitivity, EVT. What is transitivity? That means this is transitive, right? So this is the only thing that we had not used, and I'm now going to use it. X is related to Z, Z is related to X. What does this mean? This means X is related to Y is related to X. And we know that Y is related to X and X is related to W. We know from that we get Y is related to Z, W. So W is related to Y. So I have this property and I have this property, and they two are not same. They are a contradiction. We write it in this way. So I have started from somewhere and ended up proving two statements, both of which indicate false. Okay, if I assume something and start and go ahead and end up proving something false, this would mean that initial assumption was wrong. So what was the initial assumption? Initial assumption was this. So this is not true. See, this is there, but this was the initial assumption, right? So if E of x is not equals to E of y, then E of x intersection U of y must be. Okay, is this argument clear, understandable? Should I repeat it or something? Hello?
So it's clear.
Yeah. So who was the person who had asked me this question so that he could not do it? I forgot the name. Was it Soumitra Bokshi? No. Somrita Bokshi?
Somrita, sir. Yes, sir.
Did you ask?
Yes, sir.
Is it clear now?
Yes, sir.
Okay, good. Okay, so by the way, if you are a bit puzzled about this whole implications and all those things, what can we assume and what can we prove and how of that, we will be proving, we will be giving you the formal things of how to go about it. I mean, that is exactly what we will do in the next, in this class, possibly, or in the next. Yeah. So anybody has any other questions? Some other things that you would like me to discuss further? Okay, so if not, let me say what I will do today. So today we will be going into something called a propositional logic, and then possibly at the end go a little bit into something called a predicate logic. So don't be afraid of whatever is being told now. Okay, it will be a very simple statement, very simple. It will be kind of almost related to the English language and all. Okay, so don't be worried about it. But it is very important to kind of ensure that formally we know what is happening. Okay, so let me go about it. Okay, so if somebody makes a statement, any statement, okay, any statement, you can say something, right? That has usually two parts. A first part is a set of assumptions or a premise and a deduction. Okay. Now, say you say that today it is cloudy. Okay, what is the assumption? The assumptions are that, I mean, whatever you have seen now, right? That fact that today is today. So there are the universal assumptions that exist. And under that, you are saying that, oh, under these things, today is cloudy. Okay. Now, these assumptions can be composed of a multiple different statements. Okay. That can be either true or false. So just like we just did it just now, right? In equivalence relation, the idea was that if this happens and this happens, then something. And maybe one of them is false, and maybe one of them is true. Right? And similarly, the deductions also can have a lot of these compositions. Okay. So if I say that all the students who is sitting in this class has gone through the ISI entrance exam. Okay, is this statement correct or false? Okay, doesn't matter, but important thing is that if it has a assumption, what is the assumption? Assumption, so this is kind of rewritten in this following way. That if a student X has come, is attending this class, okay, this is the assumption, then this student has gone through the ISI entrance exam. So the deduction is the second part. Okay, maybe I can make some more complicated things. If a student is attending this class, then either the student has gone through the ISI entrance exam or has gone through the ISI or gone through the GATE exam. Then the deduction has two parts, right? So similarly, every logical statement, you can see it as a collection of assumptions and a collection of deductions, right? Now, the propositional logic starts from this very basic understanding that every statement, or which is called a proposition, is either true or false. Okay. So, when the X came, X is sitting in this class. Is it true? Maybe it is true. Maybe it is false. But it has only these two options. We are not dealing with any hybrid quantum stuff that, oh, it might be true, it might be false. Okay? No. Any logical statement has this statement. Every statement is true or false. Okay?
Sir,
Yeah.
sir, so I have encountered one particular statement like this statement is false. So this will be true or false? Like,
Okay, good. So this statement is false. Okay, okay. Let me finish this class. You will understand what it means. Okay, you will understand this statement. Yeah, you will be able to answer this question, whether this statement is true or false. Okay. So it all depends on certain things that we will be. Yeah, what implies what and all. Okay, good. So, okay, so these statements can be composed of certain conjunctive or connectives. So they can be and, or, not, implies, if and only if, and so on. Now, there can be a lot of such connectives depending on the language that we're talking about. So in the English language, some of the connectives might be hidden. Some of them can mean something else. Okay, maybe something like instead of implies, it can be if and then, if then statement, and so on. But basic idea is that something implies something, something and something, and so on and so forth. And these statements can have some terms. Okay, they are not exactly specified. They are called variables. We all know that there are terms like that kind of stuff, right? They're variables. Okay, good. So like here, say here is examples. Okay, that when it is cloudy, it rains. Today it's cloudy, so it will rain today. Okay, so here are these lot of things that are composed inside this. Okay. So there is a statement. Okay, so this is an and, right? It's a dot, means a full stop, means an and. So the first statement is also a composition thing, that when it is cloudy, so if it is cloudy, implies it rains. And you have also been told that today is cloudy, implies that today it will rain. Now question is that, is this statement, the individual things are a statement, okay? This is also a statement. Inside this there are things like today it's cloudy, that's also a statement. And everything together is also a statement. Okay, so the basic things can be true and false. Like things like, oh, today is cloudy is a basic statement that is either true or false. Okay, but this whole thing, the composition of statements, and that also is either true and false, depending on whether the whole statement is coming out in a correct way or not. Similarly, here say, every city in India has a horrible traffic. Chennai is an Indian city, so Chennai has horrible traffic. Same thing, there's a lot of statements there, right? First statement is a implication. Every city in India has a horrible traffic. In other words, it means that it's an English way of saying that if I have a city in India, implies it has a horrible traffic. Second one is just a statement. It has nothing to do with it. Today, Chennai is an Indian city. Okay, and third one is that it is so Chennai has a horrible traffic. Meaning, out of this, both these two together, it implies that Chennai has horrible traffic. Hello, yeah. Hello. Hello, someone's microphone is, yeah, I think that. Okay, so we will be facing this kind of statements everywhere, okay, in mathematics, in English, in things, and so everywhere, okay. Okay. Now, so every basic, so thing to note is that every small statement is either true and false, and by connecting those true and false, right, we are producing more and more complicated statements. If I connect something with an and, it means something. If I connect two things with implies, it means something, and so on. Okay. So let me, so this is what we call the rules of this game. Okay, so let me quickly go over some things here. You'll understand. So here, so think of P to be a statement and Q is a statement. Okay, and here is a function that is taking two statements and producing another statement. Okay. So this is what is called the truth table of AND. The truth table, you remember, it's a function. So maybe if I go back, so this function is basically, what is this function? This is a connective, right? It's the AND is a connective, in which it is taking two statements, P and Q. You can think of them as kind of a, P can be true or false, Q can be true or false. And in that case, what happens to the P and Q? So P and Q becomes a single statement which is either true or false depending on what the initial compositions are, what the initial functions correctness are. So if P is false, Q is false. Means I make a false statement and I make another false statement, and I say that the third one, right? So say I work in the in the Indian Army, and you live on the moon. Do you think this statement is correct or not? Is this statement true?
No, sir.
It is not true. Why? Because I have made two statements, both of them are false, and I've connected with this and. Okay. What happens if I say something like, I work in ISI and you live on moon? Is this statement correct or false? again,
False.
it is false. And the reason is that and is the kind of we have kind of defined and in such a way that both of them has to be correct, and only then it is true. Okay, but if I told you something else, that I work in Indian Statistical Institute, or you live on moon, is this statement correct or false?
Correct.
This is true.
This is correct, right? Because I am saying one statement which is correct, one statement which is false, and I have connected with an or. Okay, so it's very important what is the connective that we are applying. So if the connective is and, then this is what is called the truth table. Okay, so if both of them are false, we have a false. If one is a false and one is a true, we also still have a false statement. And the only time this connective becomes true is if both of them are true. Okay. Now I'm sure many of you are thinking that this is all, very simple. It is very simple, no doubt about that. But only by doing this simple thing, we will soon produce something pretty complicated. Okay, good. So similarly, this OR function has a truth table. So every connective is a function, right? This OR function is also a truth table of the OR function. And basically it says that only time the OR function is false is that both of them are false. If one of them is true, or at least one of them is true, then the whole thing becomes true. Okay. Now there is this thing, okay, not. I said that I work in ISI, and not of this statement is, no, I don't work in ISI. Right. So the idea is that if first statement that I say is true, then the not of P, this is a function that takes one value and outputs one value, one true and false value and outputs one true and false value. Right. So true becomes false, false becomes true. Okay. Nothing so complicated about it. And this is a very interesting statement. Okay. The first thing, so this is something that you possibly are not familiar with. Okay, what does something implies something means? So this is something similar to the question that your friend asked about this statement is true kind of stuff. It's somewhat related to, or this statement is false, that kind of statement. Okay, the first, so when actually this kind of logicians were discussing all of this stuff in the when the mathematics was being formalized. Okay, and there were a lot of debates and all those things were going on. And the first thing that told is that a true statement always ends up saying a true statement. So if I start from a true statement, I will always end up saying true statement. I cannot prove a false statement from a true statement. Okay, so this part is kind of not problematic. People accepted it. Okay, that means if I have a true statement, I cannot end up proving a false statement. Okay, so true statement cannot prove a false statement. Okay, so if you start from, so it's something like you start from something, you start from P is a prime, and which is it, let's say if P is a prime, and you go ahead and all and prove something mathematically correctly, you end up proving something that is correct, as long as you are making everything that no mistakes are done, right? But what about false statement? This was a big debate that was there. If I say a false statement, can a false statement imply the false statement? Can a false statement imply the true statement? What do you think? Can a false statement imply the true statement? Can a false statement imply the false statement?
But it can be both.
Both. It can be both. In fact, it was told that a false statement, you can take a false statement and end up proving any statement you want in the world. be it be true or false, be it be not even connected to that. So, I mean, when this one was going on, I mean, there was, I mean, those days journalists were possibly much more better than what we have now. So there was a big debate, and the journalists were not happy with this statement. And there's a famous mathematician, G.H. Hardy, and he was asked by a journalist that you are claiming that a false statement implies of anything. Then if you assume 2 plus 2 equals to 5, can you prove that you are Pope? Okay, and he actually proved it. He actually says, there is a proof, it's a kind of fun proof. The 2 plus 2 equals to 4, but we know that 2 plus 2 equals to 4. It means 5 equals to 4. By subtracting 3 from the side, we get 2 equals to 1. That means 2% equals to 1%. Therefore, you and Pope are the same person. So 1%. So this is of course a funny thing, but this is a part of this logical formulation that happened. And this is something you should remember this thing. A false statement can prove anything. Okay. So this is something very important to remember, okay? Okay. So if you suddenly see that you have a lot of things being proved, okay, some of them is correct, some of them is false, then you know that it was starting from a false statement. Okay. So this is the truth table of implies that if you have a false statement and false statement, the false implies false, yes. False implies true, of course, yes. True implies false, no, that cannot happen. And true implies true, yes. Okay, so then is also the if and only if statement, and I don't want to go into it so much. So this basically means that if P implies Q and Q implies P. It's the kind of a composition of connectives, connectives of connectives. And we have this kind of a truth table. Okay. Now, there are the other things that are there. Okay. So this is something that we kind of told. This is called this is kind of going from the world of propositional logic to the world of a bit of a predicate logic. Okay. So here is a statement P of X. So this is a statement that starts with that is true for a particular variable. Okay. And when I have something for a particular variable, it is important to kind of quantify the variable. What is that variable? You cannot leave a variable hanging. This is something that you should remember everywhere. When you are making a statement, having a variable hanging is not correct. Right? So for example, so say, if I say something like, yeah, so n square minus 1 is not a prime. Right? Is this statement true or false?
False.
Maybe true, maybe false.
Why are you so confused?
We don't know about what is n.
You have not even told what n is.
Yes.
Actually, what I meant is that, okay, what I meant is that n is any real number. And then you see that it's completely false, right? If n is any real number, how can n square plus 1, n square minus 1? What is the factor? What is the prime number mean there? Can a real number be a prime? No. The reason is that I have not even quantified it. Okay. Now, if I say that for all n, n square is equals to n square minus 1 is prime. This is a statement I've told it. But if I tell you there exists n for where n square minus 1 is prime, this is also correct. And these two functions, these two statements are not same, right? So the important thing is to notice that there is these two notions, for all and there exist, and every statement should be quantified. You cannot leave loose variables hanging. And after you have this set of, if once you define this, quantify these variables, the rest of it is called the proposition and or the predicate, and the whole thing is called the proposition. Okay. Good. Okay, so actually there is something called a universality statement, and I will not be proving anything, but you can take a look at it and convince yourself that every logical sentence can be written as a using this set of symbols. In fact, you don't need so many symbols either. Okay, but and, or, not implies, if and only if, and there exists and for all. Using this, you can write everything that is there. Any logical statement can be made using this set of connectives. Okay, so now let me try to see why is this way of formally seeing the logical statements is important. Okay.
Hello, sir. A question from your last slide.
Okay.
There you have written if and only if, but
Right.
you told that that is just
Yeah.
implies and.
Yeah. So you don't need, as I told you, you don't need all of that. Actually, you will see that and, or, and not is more than sufficient.
Okay, okay, sir.
Okay. In fact, you don't even need that. You can do it even with lesser than that. But I'm saying that these things are enough. Okay. We'll soon see that even lesser than that is good enough. But yeah. Actually, why don't you try to prove this statement? Okay. It's not too hard to prove it. Okay. That any such things or any statements can be written in this way. I mean, it basically boils down to the fact that any function, okay, so particularly here, any functions that takes two variables to one variable, it takes a true false, so true false to the power, so maybe if I, let's see. Just 1 second. So if you see this one, it says that any function f from true false square to true false okay can be written as a combination of and, or, and not. Okay, so think about it. Okay, we will soon see some ways of you. I mean, by the end of this lecture, you will see some hints about how you can go about this particular proving this particular thing.
Sir, why is that true false square? Like, why you put that square there?
Oh, because it is a function that takes two variables.
Oh, okay, like two statements.
Two statements.
Okay, okay. Thank you, sir.
Takes two statements and outputs, and a single statement.
Okay,
Right?
okay.
Sir,
Yeah.
This statement.
I want to ask a question that if we can if we can replicate the truth table of implies and if and only if with and or not, are we done with the proof?
No. see, I mean, you're not done with the proof because there are a lot of questions, right? So how many functions are there? How many functions are there of this kind?
Okay.
Can you say how many functions are there?
16. For this, there will be 4.
You got 4.
4?
Yes, sir.
Why 4?
16.
So 16, sir.
16.
Right. So what is the domain here? The domain is,
T, true, false.
yeah, so it's like a,
Cartesian product of true, false.
right, exactly, right? False and true. Okay?
Yes.
The size of the domain is 4. Right? Now, a function, what is a function? It's a function from the domain to true and false.
Yes.
So that means I can either place, oh, this one is mapped to either true or false.
Either two, yes.
This can be mapped to either true or false, and so on, right? So the total number of functions this is equals to 2 to the power size of the domain, which is, I think in this case it comes to 2 to the power 4, right? 16. Okay, so okay, one way of doing it is to basically prove that all the 16 functions can be written using this set. Okay, so this is a possibly this is doing it is kind of a bit more complicated because you have to do it with a lot of all the 16 is not a small number, but you can do it with a bit more clever ideas. You can do it even with less number of work. Okay, now I mean I know that some of you might be a bit confused of what does it mean by it can be written in this form. I will soon describe that. Okay.
So in the statement for all x p of x, here p of x is a statement.
P of x is called a predicate. So it's not a statement, right? So it is not a true and false thing because it is an undefined x, right? So this is not called a. It's a statement you can think of, but it's not a proposition. It is not a true false statement. It's a predicate. Only when you kind of quantify that x. Okay, so that quantification of x can be in various ways. You can of course quantify like this, for all and there exists. You can also quantify things like if x is equals to this, then this.
X belongs to some set.
That also is, if x belongs to some set, then this, right? Then p of x. That becomes a statement. That statement is true and false.
If x doesn't belong to some set, then in general it's a predicate for all x p of x.
If x is not quantified, if you don't tell me what x is, then it is p of x. Okay, so just like as I told you, right, this statement, right? Maybe this one, that okay, n square minus 1 is a prime. Okay. This is a predicate because this statement can be false, can be true, doesn't matter because I am not even told what n is. Right? Okay.
And n is not quantified, so we cannot say anything like it is a statement or not.
Right. So you need a quantification here. Sorry, I cannot hear you. So whoever is saying, I cannot hear anything. Yeah, once you quantify it, it becomes a proposition. Okay, so I can write it for all n, say, in natural numbers. I can write there exists a n in natural numbers. I can write for all n less than equal to 10. I don't know what. But whatever I write, it is fine. Now it is then, it has been quantified. Okay, or even just forget for all and all. So I said if n equals to 10, then that is also fine. But I have to quantify n in some way. Then this becomes a proposition. Now this is something that is very, 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 very important. Okay, because I am sure as and when the course evolves and we see a lot of new different kind of stuff that will come up, new different kind of arguments that will come up, you have to prove something. I can bet that many of you will give me proofs in which you will not even tell me what is the quantification. Okay, and then you should always keep in mind, and in that case I have complete full right to give you 0 marks for the scheme because I don't even know what you mean. So every statement, anything that has a variable has to be quantified. Okay, so I can say something like say yeah, I was giving another example, but forget that. Yeah, I think you've got the idea. Right? Good. So, right. Now,
Hello, sir. Sir, another question.
yeah.
If I want to relate that assumption and deduction part, what is the relation with this predicate?
Same thing, right? I mean, so you can have an assumption and a relation part that might have a x in it, right? So it can be that for all x, if something happens, then something happens. Okay, so predicate can also have an assumption and deduction, but you have a variable which you are quantifying. Okay, the whole thing becomes, once you quantify the x, the whole thing becomes fine. So maybe I can give you an example of this. Just 1 second. Let me see the example. Can you see my screen? I don't think so. So something like for all n in natural number, okay, if n is a prime, then so is the n and n is odd, then n squared minus 1 is divisible by 8. So the whole thing is a proposition. Now, whether it is true or false, that's not a matter, but it is either true or false. That is something we know. Out of which this is the predicate. This is the predicate because it has a variable sitting there. And this is the quantification. And inside the predicate also there is these 2 statements, and then I have another statement. So if I say this is a statement S1, this is a statement S2, and this is a statement S3, now all of them has a variable n, right? So this basically boils down to for all n in natural number, S1 of n and S2 of n implies S3 of n. Right. So this is an assumption, this is a deduction, but since it has a variable in it, so it has to be quantified. Okay. Fine.
Yes, sir. Thank you.
Yeah. Okay. So now let's go on here. Okay. So here is some examples in which you can convert a mathematically logical statement, sorry, English statement to a mathematical statement. So let's see here. So here is a statement, right? It says that if you did not know the material earlier and you don't study hard, then you will get a A in this course. Therefore, if you get an A in this course, then you knew the material earlier and you studied hard. Okay. Now, there's a lot of statements here. But if you think of it, okay, so note that this statement, what does it mean? When can this statement be true or false? Okay, so it means that this whole thing, I mean, I can put, so there are a lot of subparts, small basic propositional statements. I can put those statements to be either true or false or something, and still it should hold true. So for example, okay, say you have this statement. If you don't know this material earlier, so this is one of the statements, correct? One of the propositional statements. This statement can be, so you did not know the material earlier, can either be true or it can be false. Similarly, you can have this other statement. You don't study hard. That is also a statement that can be both be true and both be false. And then you have, I mean, then there are other statements that I have not written up. Like then you have this statement that you will not get a A in this course. This is a statement. Similarly, if you get a grade A, so forget if, so you get a A grade in this course. This is a statement, right? This is either true or false. And then you knew the material earlier is a statement again. And you studied hard is again another statement. Fine. And then there are these connectives. And then, so this therefore is another word, but it basically means it is an implication. This implication of the previous statement implies something. Okay, so it's an English way of saying it, but mathematically what is happening? So let's see, I think I have it written here. So the variables, so no, this is not a variable, you can think of variables. I mean, don't think of this to be the variables of X and Y. So this is like the variable, this propositional statements, okay? So you have it, you did not know this material. Let's call this one be P, statement P. Similarly, the statement you don't study hard, that we can call it a statement Q. Then we can have, you did not get an A in this course, let's call it PR. And then, what about this statement then? You knew this material earlier. Should we give it a new name?
Not of P.
Not P.
Exactly. So this is something we don't need to give a different name, right? This is not of P, right? So if you do the same thing, okay, and you have this, you studied hard, that is not of Q, and you get a grade in this course, it is not of R, right? And this whole statement, therefore, okay, now we can throw away everything that has been told here. Okay, I don't know, I don't care whether you, who is you, I don't know. That is not the part here, right? So the statement basically becomes something like this. You can read it out from here. What is P? So let me just read it out, okay? You did not know the material earlier and you don't study hard implies you will not get a A in this course. This whole thing implies, or you can say, therefore, if you get a A in this course, then, okay, or implies again, you can think of, then you know the material earlier, or, oh, this should be or. So this should be, I made a mistake here. This is and, right? Okay, this is and is written, let's see and. And you get an A in this, and you studied hard, right? Okay, good. See, this statement has been kind of written up in this form. And now I can ask this question. Is this statement correct? But I don't care about whether you have studied the material or not. This statement is a statement independent of you. This statement has become a mathematical statement. Okay? And now we can ask, is this statement the right statement or not? Is it a true statement? Does it evaluate to true? Does it evaluate to false? So let's see. I hope this is there somewhere. Yeah. So this statement, this sentence has basically been written here, right? And the idea is that this sentence or this statement is true if and only if, see here, for any setting of the variables to true and false, this sentence should be correct. This sentence should evaluate to true. So it is not like, oh no, see, if you put P equals to true, Q equals to false, and R equals to true, this is true. No, this has to be true for any setting. Okay. And okay, so now you have to check whether this sentence, whichever was written, whoever has told this sentence, is it logically correct? It is logically true, right? We can first convert it into this sentence and now check whether this sentence evaluates to true for all settings of all settings of the variables to true and false. This is very important, okay? And if it is true, meaning if I find out that, oh, for all settings of variables to true and false, so whether P is true or false, Q is true or false, R is true or false, this whole sentence always evaluates to true, then this sentence can be, we can call this one as a theorem. That's a fact. That is true. Okay. Now, I find it a lot of times people in normal conversations and all will make such really weird mistakes. And they will have a deduction, make a complicated argument and deduce something else. Right? Are they doing correct? Whatever they're saying, is it correct?
Sir,
yeah.
So the theorem part, what you said, can you repeat that?
Okay, so if this sentence is true, what does it mean? It means that for any P, Q, and R, this thing is true. Okay? This thing evaluates true. I'll soon show it, I think, here. Okay? In that case, this whole thing becomes a true statement, universally true statement. And this is we can call as a theorem. Okay. So let's see here. So how do you check whether something is true or not? This is something very important. And to do it, one of the most kind of brute force way of doing it is to keep on writing it in terms of the truth table. So let me just do it here. So here is this function f. Okay, this f becomes a very complicated function. This function, right? And I have p, q, and r. And p, q, and r can take all the 8 values. sorry, all the, yeah, I mean, there are 8 possibilities, right? P can take 2 values, Q can take 2 values, R can take 2 values. And the question is that is it that for all values of P and Q, what is the function value of R, F? Okay? And so do so, we can, I mean, here is a kind of a step-by-step way of doing it. Okay, so we can think of this part as S, this part as T, and then the F basically becomes S implies T. Okay, so such kind of stuff we can do. And okay, actually forget this S, so there's a bad notations over here, but this is written here. So say I can have P and Q, so P and Q can be called G, okay? And this whole thing therefore becomes G implies R. And then we can have this not P, not Q, not R. And similarly, we can write this stuff, P prime and a Q prime. And then we can have this whole thing as R implies this H. And F is basically, so this should not be, right, this is actually correct. This is S implies T, right, sorry, I made a mistake. Yeah, so tell me, somebody was saying something?
Sir, if we could convert the implied sign in terms of and, or, and not,
I will do that, I will do that.
we can.
I'll come to that. You are right, you can do that. You can, so this is one way of trying to prove that F is true or false, okay? So, and if you get some, I mean, here is a kind of a, you go and prove it to yourself that you can one by one keep on doing it, and at the end of the day you will find out the truth table of F, right? And what you will realize is that, oh, this function F or this statement F is false for certain settings of the P, Q, and R. Which means if I have to go back, that this sentence, if somebody had given you this sentence, he was not saying correctly. Okay, he was not logically correct. So whether a sentence is logically correct or not, this is what will help you to find out. Okay? And this is not just for English sentence or something. Any argument has this thing. Any logical statement has this thing. And this is one way of verifying whether a function is always true or false. Okay?
Hello.
Yeah, hello.
Sir, can you please show the previous slide? The previous slide.
This one?
The previous slide. Yeah. So actually what we are doing here is that, sir, we are not checking whether this statement is true or false. We are actually checking whether this statement is meaningful or not.
Same thing. That's
Sir,
what it means.
So actually there is not, so it's not a difference between checking whether it's true or not, or whether it's meaningful or not.
This any sentence, if somebody says, what does it mean, meaningful or not, right? If I say that if n is n prime, then n square is always divisible by n square is divisible by 8. Either you can say this statement is true or false, or you can say this statement is meaningful or not. It's just an English language way of saying it, right?
Yeah. Yes. Okay.
Just I mean, don't be confused with English language and math. Okay, I mean, English language possibly has subtle ways of saying things, but they actually mean something same. Okay, logically it means same. Okay, good. So since this expression does not evaluate to true always, we cannot say this expression is correct or not correct or false, whatever you want to call it there. Okay, I will also use this correct, false, true, all of these things at various times. But but they mean all same thing. Okay. Now, so this brings us to another thing. Like we have to check whether two different expressions are correct or are same or not. Okay, there can be different expressions. So in some sense we have done it here. So there was this expression here, and what we wanted to check is that is this expression same as some other expression which is always correct? So how do you do it? Okay. So two statements are equivalent if they evaluate to the same thing, if the truth table are same. So for example, if somebody says A implies B, okay, or if A then B, this is same as saying if not B and A then false. Okay, or in other words, if so not B and A is a contradiction. Okay, this is exactly something that we did in the beginning of the class. We wanted to prove A implies B. What we did, we said, okay, let's say that it is not true. So B doesn't happen. And let's say A happens. So it is not B and A. And we went on arguing something and said, oh, see, you have found something which is false. Okay, therefore we have ended up proving A implies B. Note that this is just a mathematical way of saying exactly what we did in the beginning. It is a proof by contradiction. We will come and formally say all of these things later on, the various proof techniques. But this is what we have done so far, also in the beginning of the class. Right? So how do you prove this statement? So, I mean, it's kind of intuitively clear, yeah, it mostly seems fine. But if the statement becomes much more complicated, the A or C implies B and D, such kind of stuff, you are very confused. What is this statement? And so somebody else proves something else. So the best way of doing it is actually to write up the truth table. Say A implies B and this quantity. And we can find out this truth table for A implies B. We can write down the truth table of this quantity. And what you see is that we have these two truth tables and they are identically same. Okay. So if I give you a function, if I have two functions that evaluates in that looks different, okay. So somebody comes and says that, okay, consider x square minus 1. And somebody comes and says, no, it is consider x minus 1 into x plus 1. You know both of them are same. Why are they same? One of the things that you can say these are same is because take any x, it will get evaluated to the same thing. X square minus 1 would be exactly same as taking x minus 1 into x plus 1. Right? So we don't prove it like that because x can take any real numbers and so on and so forth, right? But here, since the domain is finite, we can say something like this by looking at the truth table itself. Okay. Okay, so let me just see. Okay, good. So this is an equivalence thing. Now there is another way of doing equivalence, and that possibly you guys have already seen it in some sense. So I will kind of talk about it a bit later. Is basically using the some other kind of manipulations.
Excuse me, sir.
Yeah.
Sir, one thing I want to clear that not B and A equal to F, this equal to is comparison.
No, so this basically means that, okay, that this means that you take not B and A, you end up proving a false statement. Or this you can say not equal, you can say implies false. Okay, so this is, it's not equal to, this is an implies or if and only if false or something like that. Okay, or basically this statement, not B and A. Okay. I mean, you can think of it as like a if and only statement. Okay, so this is true if that is true, if this is false, if this is false. So whatever is written here, you will realize, okay, will be the, this is the truth table of not B and A. Sorry.
I think, sir, this is basically truth table of if not B and A is equal to, I mean, if not B and A is false, then it is true.
Yes, it's not B and A is false. Yeah, it's equal to, yeah, great.
Yes, that means a comparison. We are doing the comparison. If comparison is right, then it is true,
Yeah,
or
this is if and only. This is if and only. Think of it. This is if and only, meaning whether this one is exactly equals to F or not. So for example, in this first one, not B and A is false. Okay. So let's say not B is true, true and false is false. But false is equals to false, or false is if and only false. So true. Similarly here, not B and A is, again, not B is false. So false and false is false. So it's equals to false. Yes, it is equals to false. What about here? So here not B and A. So not B is true. True and true is true. So this one in this particular thing, this one evaluates to true. But is true is equals to false? Or true if and only false? No. So this is false. So this equality is, you think of it is if and only.
Sir, I mean, if it is, if we say is at as equality, then what will be? I mean, what will be the problem? I mean,
No, nothing. I have not even defined equality in this sense,
okay,
right?
okay, yeah.
Yeah. Okay, I have not yet defined equality. I mean, it is not equality, it is if and only.
Okay, sir.
Yeah. Okay, so so here is something that we will be doing, possibly not this class, but in the next week possibly, that we will be kind of trying to prove A implies B. Okay, and basically means that you assume A and then prove B, and question will be that is this true or something like that. Okay, how to prove if A then B? So this kind of stuff we will soon see that how to give this proof using various techniques. Okay, so I will come to this one, so I don't want to go into this particular part right away. I mean, there are, I mean, if you can just think of things like you have seen the proof by induction, proof by contradiction, proof by so on and so forth. All of them will be coming up in this particular model. Okay, so here are some problems. Yeah. Hello. Oh, is there any book that you should follow? No, unfortunately enough, logic doesn't have a book that is there to follow. I mean, there will be some, I mean, you can find this one in any, so better it will be, look at my notes here. And if not, I will search in the internet for any propositional logic. Whatever we are doing is very simple. Okay. And we will give you a lot of problems to be done. And yeah.
Sir, earlier I had followed the Rosen book in my undergrad level.
Okay.
That's why I'm asking.
So you can do that. I mean, any book is fine. Okay. So whatever we are going to do right now is very simple. Okay. So it will be there in almost any book, or it might not be there in some books also, because so many of the discrete math books might not even have propositional logic, predicate logic. Okay, so here are some problems that you can try to do yourselves. Okay. So what we have every statement or proposition is either true and false. We have the statements can be done by connecting them. I mean, I have written here with 5 kind of connectives. You can do it with even less number of connectives. Okay. A statement can have some unspecified term that we call variable. And to prove the equivalence of this one, okay, we can do 2 things, right? So what is the thing that we kind of do? We can either use the truth table notion, right? This is something that we just now saw. But how do you prove that x square minus 1 is same as x minus 1 into x plus 1? You don't go and proving it for every x these 2 values are same, right? You use some kind of a operations that are known to us, that oh wow, how to multiply x minus 1 into x plus 1 I know, right? So these similar things are there. So instead of using brute force, we can simplify formulas. And just like in the algebra that you have seen, that you know, that you knew about how to simplify certain things and all, here also there are some set of rules. Okay, and here is the set of rules that you can follow. Okay, now I'm flashing this set of rules in one shot. Do you guys see anything related to this one earlier?
From set rules.
Right. This is
Set
exactly
similar to the set rules.
This is exactly analogous. In fact, if you go and open your slides from the previous class, everything there was, this one was an OR, meaning an union. And this is an AND, meaning a intersection.
Intersection.
So now you see why this is, symbols are also like this, AND OR. Right? And you have this negative thing. So just like you could prove those things, I mean, these are kind of a thumb rule. So it's like somebody has ended up proving these statements. Easy to prove, right? How do you say, if I ask you how to prove this, how will you do that? You can write the truth table and work with it and prove that, oh, okay, this one's truth table is same as this one's truth table. Right? And so once you have done with that, you can now use this set of rules to simplify things. Okay, so they can do things. So in fact, I will ask you guys to go back and prove that this statement that we had is actually false by, instead of using the truth table technique, to prove it using the rules technique. Okay, and this is a problem that we will, so there are a lot of this kind of stuff. All of them, I would like you to prove it using truth table and also using the set of operations, the various these rules. Okay. Now there is only one set of rules that has to be kind of told to you very specifically. This is something that we will use a lot in sooner or other. Is that what happens if I have a predicate like this? Like I have a for all x. What is the negative of this for all? This is something you should remember, this one, that a negative of for all x.
No.
Sorry. So to get the negative of for all x, okay, you first invert for all to there exist. And then you take the negative of p of x. So not of for all x p of x is same as there exists x of not of p of x. The crucial thing to remember is that I don't change this x. So if this one was, if x is in a particular set, so for all x in S, it still remains for all there exists an x in S. Okay, this variable is untouched. Note that. The quantifier in before gets flipped, okay, and the predicate is negated. Same as here. Now, you can try to convince yourself why is this the correct rule to have. Okay, I will not go into it. You can prove it actually. Sorry?
If we have a statement not of for all x there exists y, p of x comma y. So then
not of for all x
there exists y.
For all
P
y.
of
No, just 1 second. Let me just write it down. I cannot follow. Just 1 second. Yeah, so tell me.
Not of for all x.
Not of for all x.
There exists y.
Good. P of x.
P of x comma y.
Okay, good. How do you do this? The best way of thinking of it is just think of it one by one. Okay, this is a for all x, and then you have, so there's not of this, and then there exists y, p of x comma y. Right? So, and this term, y is defined, so it is not, y is no longer a variable. X is the variable, so this is the predicate with x being the variable, and there is a not of for all x. So what should this be? By our rule, I should flip this and for all to there exist. Let x be x, and then I have to take a not of there exists y, p of xy. Okay. Now this one again, there exists x. Now look at this part. This will be for all y, not of p of x. Okay. So this is something that you have to be very careful. This is something that we will need it again and again and again. Okay. So this rule of qualifier is very, very simple. So good, I think I will stop now. Okay, so with this I have kind of defined you the propositional logic, what a statement is, how to convert, how to invert, how to move a proof from one English statement, how to get a mathematical statement, okay, and then how to check the correctness of that statement, at least in the Boolean world, in the truth table world, and then how can you do it using some set of rules, and then how to take a then various things. Now, in the one thing that I usually give, so this year I was not a part of the admission committee, but when I am part of the admission committee, I usually ask the MTech students in the entering batches in the interview or even in the questions, a simple thing like, I will give you a complicated English sentence and I ask you to, what is the negation of this statement? Okay. Now that English sentence can be a plain English sentence, it can be a theorem, it can be a mathematical statement from something, but I ask what is the negation of this? So if not, then what? How can you write? Now this is very important, okay? One of the things that I expect from a student who has, with a reasonable understanding, is that what is the negation of a sentence? Okay, and you guys should try to write something of this form. Okay, or practice it. So I don't know whether, so you guys have access to the last year's MTech exam?
Yeah, sir, there was a question. I just remembered.
Yeah. So I would like you guys to think about the problem. Everybody go ahead and and whoever just now answered, if can you just maybe post it within your group or something like that, that this is the problem. Maybe you could post it in the classroom that this is the last year's MTech entrance exam and there is a problem there. What is the negation of a sentence? Okay. Try it out. I will give you more exercises, of course, on this, but this is something very, very essential. And I'm sorry to say that many times, even our PhD students make mistakes there. And that is just not acceptable. Because mathematically, when you're talking about it, if you say some statement, you should know how to take a negation of that. That is like a basic thing. Right? I mean, basic idea is that I know the answer of every or I can answer all questions. What is the negation of this? If somebody says that I can answer all questions and you are trying to convince them.
So I cannot answer at least one question.
Right. It's very important to know that it means that there exists a question. Sorry, I cannot hear you. Whoever is saying, can you just maybe write a message or something? It's very disturbing.
There exists a question which I cannot answer.
Right. There exists a question which I cannot answer. Okay, this seems very simple. But I mean, when there are lots of complicated nested stuffs and all, it can be very complicated. Okay. But note that this statement, you should not ever make a mistake like this, that I can answer all questions. Negative of that, I cannot answer all questions. I should say it again and again. This one is wrong. Okay, this is something you should remember this very much. Okay, of course, it looks like a child's play in English language and all, but mathematically, if you cannot negate a sentence, it is like your logical thinking just not working. So what I will ask you is that go and just for the heck of it, play with yourselves or friends or look at the internet and all, find out some statements. Doesn't matter whatever it is, and try to negate it. Okay. Practice it, and then you will be able to understand. Okay, good. So I think I have taught for a long time. So you guys have any questions? I can be happy to take some questions. If not, I can stop.
So one thing you can just again tell us the thing that how a false statement implies to the true statement. I mean, that part.
So I mean, how it true follows it. So this is something. See again. I mean, philosophically, the idea is that a false statement can imply any true statement. Okay, and there is no proof of it. This is something you can kind of the logicians have come up with it. So you can think of it. But a best example is what I just now told, right? That if you can prove that 2 plus 2 equals to 5 implies you are Pope, possibly you can prove anything. And that is actually true. I mean, a false statement, using false statement, you can end up proving anything. You can, false statement implies true statements, false implies false statements, false statement implies every possible thing.
Hello.
Yeah.
Sir, I have one question. So, sir, regarding that, just the previous slide, so I can answer all questions if this is the statement.
Yeah.
So, suppose the statement is I can answer all n questions. So, suppose the number of questions is n, and the statement is I can answer all n questions. So,
you say that I can answer all n questions.
Yeah.
Okay. The answer will be again, there exists a question which I cannot answer.
Yeah, sir.
Cannot be I cannot answer all Okay, if you say that I cannot answer all n questions, this possibly makes sense because this is like an English sentence that has some. I mean, this basically the way in which English language is set up, that this is actually kind of meaning this sentence only.
But so one more thing, sir. So suppose if I'm saying one more sentence, which is I'm asking whether that sentence will be a negation of this or not.
Okay.
So that statement is, I can answer at most n-1 question.
That also is a correct negation of this. Okay.
Sir, I have one doubt.
Yeah.
So the statement, this statement is false, is actually false. This is a false statement, right?
Which one?
This statement is false. So this itself is a false statement.
This is a false statement, and therefore it can mean anything.
It can be anything. And what is the negation of this statement? So this statement is true.
This sentence is a false statement. What is the negative of this sentence? Okay. Yeah, you can think of it that way. Yeah, that would be the right thing. Yeah. Okay, somebody asked me this question. I have answered all questions. What is the negation of this? See, that's what this is what exactly we are talking about. What is discussed? Subinoy Hatai, I didn't get your answer. Question.
Sir, actually, I have answered all questions.
I am not getting you. Huh?
Yes, changes to past tense.
Oh, but that is fine. I answered all questions. The negation of this one will be that I did not answer. I mean, there exists a question I didn't answer. Okay. So, like, if somebody comes up and says that I have answered all the questions in the exam, okay, and you know that that person is lying, do you mean that this person has not solved any question? Of course not, right? You'll say, oh, there is that means I'm sure he is lying. So there must be some question that he could not solve. Right? So this is the basic thing. Okay, it's very simple when you think of it, but just that overall it comes out to be a pretty complicated stuff. Okay. Okay. Any more questions? Okay. So by the way, I should say, I mean, let's stop here today. I will be happy to take questions tomorrow because there is a class tomorrow at the same time. Okay, it's a class from 2 to 4 at the same time. Any TA is here right now?
Sir.
Tommy, you're there?
Yes, sir.
Okay, can you just post in the classroom just one notice that tomorrow there is a class from 2 to 4?
Okay.
Okay.
Yes. Okay.
And yeah, so we will have, and we will go into, we will look some more stuff. So again, whatever is being done in the first week, it is very much the groundwork required. Okay. So they're not complicated. They are it is expected from any students almost. We are just kind of brushing up of things, making it formal, making it fine and all, and then we will go into. From the next week, basically, we will have one much more non-trivial discussions that will start. Okay. Okay, so I think I will leave now. I have another meeting at 4 o'clock. I don't want to also go for too long. So someone called Rabindra Sindhya is asking to repeat whatever I have said just now. I think he has lost his connection. So I let you guys do that. Okay. So I'm closing this thing, ending this meeting.